Hi, I'm Nate. I'm a software engineer at Instagram. I work on our client infrastructure team. I'm here to talk about how we significantly improved the build speed for our iOS app. So this starts out in 2020. It was a big year. Instagram turned 10 years old. So 10 years ago, Instagram started out with Feed, but over time, it has grown to include more features. It's features like Explore, Stories, Direct, and most recently, Reels. 10 years of product growth also meant 10 years of code-base growth. So product engineers love looking at graphs like this. The line's going up, people are using the app. Infra engineers, on the other hand, view graphs like this a little differently, especially when we add some labels to the y-axis. So this kind of graph is what we saw after 10 years of Instagram's iOS code-base growing. We had more classes, we had more libraries, we had more lines of code, those libraries had more dependencies between each other, and our build times had gone way up. When I first joined Instagram in 2017, I remember being able to build and install the app in about 20 seconds. But by 2020, this time had increased to about 2 minutes. We interviewed senior product engineers for qualitative feedback about how this affected their work. While we knew that the numbers were large, product engineers told us it was actually much worse than the numbers showed. The times were so slow that they would lose their focus and lose even more time to distractions. So here's what I'm going to cover today. First, I'll talk about the distinction between initial and incremental builds. I'll then talk about how we improved our incremental link time by splitting and parallelizing our product code, and finally how we scaled this to product teams across Instagram. So initial builds are the first build an engineer does after pulling new changes. It's usually done once or twice per day. Now, these builds need to download a lot of artifacts from our build cache, and that takes a lot of time. It depends on their engineer's internet connection as well. Incremental builds happen when an engineer makes a change and then wants to see it on screen. And it's very disruptive, like we saw earlier, for that to take minutes. And based on the feedback that we received, we knew that this was what we needed to focus on. Initial builds aren't as much as a problem. While they do take a lot longer, engineers do know it will be slow, and it only happens once or twice per day, so they can check their email, they can grab coffee, they can review other engineers' code while an initial build is running. There are what we call workflow workarounds here. So we knew we needed to improve incremental build time. Now we need to know, why is it so slow? One idea is that it was due to the amount of code we needed to compile. So the codebase had grown so much, there were so many more files. But it wasn't compilation. At the time, our codebase was still mostly Objective-C. Objective-C has a lot of disadvantages compared to Apple's modern Swift language, but compile times are not one of them. Objective-C compiles very quickly, and it's very parallelizable due to the use of header files for imports. On an incremental build, we're also only compiling a few files, sometimes only just one. When we looked at a trace of the time spent in an incremental build, we found that most of the time was spent linking and bundling. So linking is the step that combines all of the compiled files into an executable binary that you can run on an iPhone. And bundling is when that binary is combined with resources, so that's things like images, string translations, into a full iOS app that we can actually install on an iPhone. This work was done from scratch on every build. So while most incremental builds only compile 1 or 2 files, all of the linking was redone for the entire app. And even when we have to do more work in this compilation phase, we're able to parallelize it because we have so many different source files. That wasn't the case at all for linking. Okay, so we knew we needed to reduce linking time on incremental builds. Now that we'd identified the main problem, linking, how do we fix this? So we have one big binary containing all of the code in the app. Linking can be broken up by creating what are called frameworks. Rather than having a single binary, some of the code is added to a dynamic library that the binary loads when the app starts. In incremental builds, we're then able to skip relinking the framework if none of the source files that go into it have changed. We can take this further and divide it into more frameworks. So Instagram, the binary, would get smaller and faster to link. Okay, but how do we decide what code goes in which framework? The first option is to do it manually. So source files are grouped into libraries. We could then manually assign either individual source files or libraries to frameworks, and this is how it works in traditional iOS development with Xcode. You create a framework target in Xcode, and then you can directly just add source files to it. You set up your dependencies between frameworks in Xcode. This is something any iOS engineer will be familiar with. But we don't use Xcode directly for building the app. We just use it as a development environment. But this would translate fine to our build system that we do use called Buck. However, we decided manually wouldn't work for us. Instagram is just too big to assign the code manually. We have thousands of libraries. We have millions of lines of code. The list of assignments would be huge. Engineers would need to actively decide when they add a new file where that file should go, and it would add overhead to the development process and create opportunities for making mistakes. Our features are also very tangled, so this is just a subset of what our dependency graph looked like when we started this project. Each dot here is a library, and I've color-coded them by the feature. So one feature is direct, one feature is feed, etc. And while libraries do tend to cluster together within a feature, there's many bidirectional dependencies between features. Another option would be to develop an algorithm that we could run on the dependency graph. However, we decided that trying to do it automatically by an algorithm would not work well either. Seemingly small changes could drastically alter the entire dependency graph. It would be easy for an engineer to accidentally break something, and it would be really confusing for them to debug. This isn't the kind of thing a product engineer runs into on a daily basis. We also didn't think an algorithm would even work that well. Since everything is tangled, how do we break that up automatically? We can't have dependency cycles between frameworks. It just doesn't work that way. And we really want to get to a point where we can have parallelism. And that might not actually be feasible with this existing tangled dependency graph. So we decided to use the structure of our code base. At Meta, we use a single monorepo for all of our mobile code, and it's called FBSource. In the root, there's a folder called xplat, and that's for code that we share with Android apps. There's then a folder called fbobc, which is where all of our iOS code lives. That also includes Swift, it's just a very old name. Within fbobc, we have a folder called libraries, and that's for code we share with other iOS apps, like the Facebook app. And then finally, we have a folder just for Instagram. So taking this a.framework and b.framework idea, we turn that into frameworks for the xplat and fbobc directories. Most of the Instagram code stayed in the main binary. Code added to xplat or fbobc libraries was automatically added to the appropriate framework. We then added dependency rules to prevent dependencies on fbobc from xplat and on Instagram from fbobc. So if a violation was introduced, the build would instantly fail locally. This gave engineers immediate feedback when their change would not be allowed. So time-wise, that splits our linking up about like this. xplat takes a really long time to link because it contains a lot of complicated C++ infra code. We can't use Objective-C really in xplat because we're sharing the code with Android apps. Fortunately, this is the directory that Instagram product engineers touch the least. So on most builds, we're able to skip that, and often the first two parts, and we're only doing about 30 seconds of linking. So checking in with where we started, that looks pretty good for 4 years of code growth. Hey, it's only 10 seconds slower. Except that's just the link time. The overall numbers still look like this at the end of 2021, so we still need to do a lot better. Okay, now we need to bring down the Instagram binary more. What is in here? So what's left is a lot of product code. We have all these different features that I talked about earlier. How would we decide what order this should be linked in? Does stories come before reels? Does reels come before feed? The only way that really made sense is for these to be linked in parallel. It gets rid of this which first question, and it will also just have the best performance. We can use multiple cores to link at the same time. So these frameworks would fit in here after all of the other frameworks we already have, but before the main binary. The binary just always has to come last. That's the way it works. But okay, let's go back to this. Our features are very entangled. We also didn't really have any structured organization for our product code. Some teams created folders, others put hundreds of libraries in the root here. There's no guidance or strict rules on this. The folders didn't do anything, so you could just put code wherever. We started first by finding our own Instagram-specific infrastructure libraries, and we moved those into a folder that we called core. To do this, we mostly just used an eyeball test. The library names are pretty obvious. If it's IG Analytics, IG Networking, it's pretty obvious this is generic infrastructure and not something just for one product. So we added build time dependency rules again for the new core directory. Instagram code outside of core could depend on code inside core, but not vice versa. If a dependency on a non-core Instagram library was added outside of core, the build would immediately fail. This test was another way that we could move libraries into core. If a library didn't have any remaining non-core dependencies, it was a candidate to move. But we'd still need to look at it manually just to see that it was really cross-feature code, not product code that happened to not have any dependencies. So we're also able to move this code into a new framework, the core framework. A common problem that we found when doing this was something that we named dependency magnets. So this is core app infrastructure like URL routing or push notification handling that had grown to depend on the entire app. If a feature needed to integrate, it was imported directly and then it was called. This code was really not well structured, so typically there was a very long if-else chain checking a string for each product case that was handled. These files tend to start out simple and it doesn't look too bad, but then as the product grows in complexity, the files also grow in complexity. Eventually, it just depends on the whole app. We needed to get rid of these. So we replaced them with an internal dependency injection framework that we have that allows us to inject features at build time without explicit code for each one at the call site. This inverts the dependencies between infrastructure and product. Now the product code depends on a shared interface for infrastructure. These injected features then get tagged with the correct string key for their feature. So for URL handling, it would be part of the URL. And the infra can then call out to them without knowing the exact code that it's calling. So removing core made Instagram a little bit smaller, but we have a lot more product code than infrastructure code. Next, we needed to pull out one of the products. When we pull the first product out, it would look like this. Each product is a small part of the whole. So we also need to do this incrementally. Remember, our dependency graph looks like this. There's no way that we can refactor all of this code at once. But we had to start somewhere. So we broke some dependencies, pulled out a small amount of code. Like with core, we also set up the dependency rules. So product code could depend on product code from the same product, could also depend on core, but it can't depend on code outside of the same product. The rest of Instagram could still depend on the product's code because it comes afterwards in the linking step. Then we pulled another small amount of disconnected code out. And for the first time, we had linking in parallel. It all worked. The app built, it ran. So most of the code is still in what I'll call the remainder. This code was still getting linked every time, and while we proved the theory, it's not actually that much faster because we haven't moved that much code. In the future, once we moved all the products, then it would look something like this. Everything's in parallel. Linking is very fast. We use every core on the machine. So we did the small initial work on our own, but this wouldn't scale to the entire code base. We're just a small team. There's too much code to refactor. We need to evolve the product teams that own this code. Product teams, of course, mostly work on the product. They have time for refactoring improvements, but it's not infinite. And they have plenty of refactoring ideas to go around in their own code base. If they do this work, what would they get in return? Ideally, everyone just does it at the same time. And so everyone gets this, really fast builds. But unfortunately, it's just really hard to get every product team in a large organization to commit to doing a single project all at the same time. In practice, the initial volunteers get to join the frameworks before the Instagram remainder, and unfortunately that's not actually faster for them. It's a little bit faster for everyone else because other teams can now skip relinking their code that has moved out, but the team that did the work is still linking their code, and then they're linking the remainder on every build. So not much uptake on this. Not a great reward. We needed a different approach. All right, back to the remainder. Well, what if we go in the other direction? If we put the product code after the remainder, then teams whose code lived there would skip linking the remainder. The problem was that the remainder is the Instagram binary, and frameworks just need to come before the main binary. That's just how it works. But this was easy to solve. We could just put the remainder in another framework, and then we just have a tiny binary at the end. So while we're still linking this binary on every build, because it's so small, it links very quickly. We barely even notice it. So we still have this problem, but now we're attacking it from a different direction. Before, we were breaking dependencies on the remainder from a product. Now we need to break dependencies from the remainder on a product. This sets up the right incentive for product teams. If they did the work, they would be immediately rewarded with faster build times. The more code that they moved into their product framework, the higher the chance that one of their builds would be significantly faster with the remainder removed. The idea was still unproven, though. We had a strong belief it would work, and that the improvement for the first product team to do this would be huge, but we didn't have any specific example to point to yet. So we convinced the Instagram Direct team that we should have what we called a modularity sprint. And we set up with them for a week and broke dependencies, the end result being direct framework. We moved everything at once to get an idea of the improvement, and it worked. 2 weeks later, the direct engineers were linking only the direct framework 45% of the time. We called these fast link builds as opposed to slow link, and we saw that they were 50% faster. So this got us to 19 seconds if it was a fast link build. So it worked. We got back to the 2017 numbers. What next? Well, we just needed more fast link builds, and so it turns out that infrastructure engineers can like a graph like this. Next, we need to scale this up to more teams. And now that we have the direct example with actual numbers, we had something to point product teams at, 50% faster. So we set up dashboards that teams could use interactively to explore their build speeds and see improvements. We could also detect libraries that were eligible, and we could even automatically change the code base. But we needed to be careful here because we don't want to move things that are eligible but don't make sense, right? It's the zero dependency library case again. We also added suggestions and warnings to our continuous integration system. So when engineers added a library or changed dependencies and something could be moved into a product folder, we would suggest that. So where are we today? We now have 31 products. Every one of them can link in parallel. This situation has improved a lot. Here's an updated dependency graph using only a few of the products. With all 31, it basically becomes unreadable. Each large product has internal dependencies, but there are zero cross-product dependencies. There are also some satellite libraries that you can see floating around on the periphery. These are very simple libraries that integrate only with the build time dependency injection framework, so no code depends on them directly. This is really helpful for build speeds. The linking layout now looks like this. We still have the remainder. It's still there, but it has become much smaller. And this actually, now that we've gotten this far, helps all teams, even those that haven't moved their code. So if teams are working in the remainder and they don't get a fast link build, they're still benefiting from the parallel linking of code that used to be in the remainder. With these 31 products, we're now up to 35% fast link builds. They're not as fast in relative terms as they used to be, but they're still just as fast. Non-fast builds have also become faster because we're shrinking the remainder, and eventually we expect these builds to entirely disappear. These build speed reductions have significantly improved iOS product engineers' experience at Instagram. To learn more details, check out my blog post on the @Scale site. Thanks for listening.